Okay, so the third and final part of chapter 2 is to do with seismicity, basically earthquakes, and we'll do a bit about prediction, preparation, and protection of some of the hazards as well. But let's start off by looking at the basics. Some of the key sort of definitions here. Earthquake, seismic waves, focus and epicenter. Well, you should know those for GCSE, but the difference between an earthquake and a seismic waves are the energy moving out from the focus, whereas the earthquake is the vibration of the Earth's surface due to that rapid release of energy. It's just a little thing that some people get confused there. And then elastic rebound theory is another sort of key concept that we need to understand. It explains how energy is stored in rocks. So basically it's like an elastic band. Rocks bend until the strength of the rock is exceeded. So basically, like, you can pull an elastic band until the strength of the elastic band is exceeded and it snaps. But in this case, the rupture occurs and the rocks bounce back to the underformed shape. The energy is released in waves that radiate out from that fault. So basically, rocks will then snap back to where they were originally. Okay, they go back to their underformed shape. So that's elastic rebound theory for you there. And that leads us on to the different types of seismic waves, okay? So we need to know this because the velocity is really important, and we can learn a lot from how the velocities of the waves change as they move through different densities and so on and so on. So that helps us to map the inside of the planet. So they can be broken down into 3 different types. First of all, literally first, primary waves or P waves. These are the fastest ones. They travel through solid, liquid and gas, okay? And these are a compressional wave, like a accordion or concertina or something going in and out. So they are moving in the same direction as the seismic wave is traveling, okay? So compressing in and out. So being squashed in here, stretching, squash, stretching, squash, stretching. And then we come to secondary waves. Now these come second. They are slower, okay? So all of the S's. And even more of the S's, they only travel through solids. And they're called shear waves. So this is like when you get like a spring or something and you kind of shake it from side to side. It's that movement, okay? So that's how they're traveling through the ground. And then they reach the surface. So these are the slowest of the waves. So these are called body waves, P and S waves, and these are slower. And these will roll and go side to side, and these are what seem to take out the buildings. So we've got ones called rally waves, which is that kind of motion, up and down, and then love waves go side to side in the surface as well. So this is like it's spreading out on the surface. So just some images for you to look through there. So those are your different types of seismic waves. And obviously, those can lead to different types of hazards. So we have got lots of different destructive effects. Now, this is really important for Haiti, which we'll come on to in the case studies later on. But the sort of amplitude of waves depends on what they're made out of. So really solid, like solid bedrock, will have an earthquake, but the looser the sediment is, the sort of bigger those waves become. They have greater flexibility. So Haiti was really bad because it was like near, well, it's a port, Port-au-Prince. So they had unconsolidated materials, especially down near the port, and that led to a lot worse sort of impacts than you would expect from its distance there. So first one then is the shaking. Earthquakes don't kill people, buildings do, and that's because they are moving with the ground displacement. That's the ground shaking, okay, ground displacement, it going up and down. And that can lead to things like subsidence, where buildings sink. And that can be like part to do with liquefaction as well. So this is like when you stood in the beach, you wiggle your toes and your foot sinks down. That shaking of the earthquake, when there's water in the soil or whatever, that brings the water to the surface and the sediment kind of sinks down to the bottom, kind of like quicksand there, and you can often see like water shooting out of the surface. Then after the shaking stops, it'll go back to normal. You can also have fires from broken glass, gas pipes, or electrical fires. You can have flooding, especially if there's been like damming or levees, man-made ones, or it can lead to tsunami, obviously, and landslides being a very key one if it triggers that, which can have big secondary impacts. So they're your main earthquake hazards from that. Now, how do we measure earthquakes? Well, first of all, we use seismometers, which are fairly prevalent around the world, and these produce seismographs. And on that, you can see the P wave, these small but fast ones, the S waves getting much bigger, and then your surface waves coming in as well. So that's what's happening. It is basically a ball on a chain, and it moves with the ground movements as well. And we can measure earthquake size in sort of 3 ways, but kind of on 2. So magnitude or intensity. So the first one, the most common one to us, the Richter scale is measuring magnitude of the ground displacement. Okay, basically it's measuring how much does the ground move. And it's a logarithmic scale, so it's quantitative, unbiased, okay? And each like movement up the scale, so 1 on the Richter scale to 2 on the Richter scale, that's actually equates to a 31.5 times increase in the energy from that. So for example, from 5 to 7 on the Richter scale, that's an increase in energy of 992 times as much being released. So that's the Richter scale. The second sort of one that's sort of taking over from that is the magnitude of energy rather than the ground displacement. And this is called the moment magnitude scale, MMS it's shortened down to. So the Richter scale, like I mentioned, bases it on the seismic waves. This bases it on the energy that we just sort of talking about. It's considered to be more accurate. It's also quantitative. It has a bigger sort of scale with that as well. By the way, the Richter scale, we tend to think of it going up to 10. It can actually go up to whatever we need. We just never got past 10 as well. But this can show things much more accurately, especially on the lower levels. We can get much more accurate data from this one. So this one is taking over sort of in the last 30 years. And then the third one, the intensity, the Mercalli scale. So this is to do with damage. It's 1 to 12, but it uses Roman numerals. And sort of decides that. Now this is qualitative. So the intensity, the damage that you'll see is a function of the energy, the geology, what it's actually made for, and the 3 Ps put in place as well. So this one is really important because it's a measure of the quality of life and how that's been destroyed or disturbed by the event itself. In an ideal world, they should invent a scale that is qualitative and quantitative mixed together, because yeah, it's all very well there being a 7 on the Richter scale or moment magnitude scale or whatever, but that might not have done any damage. People might just be walking around as normal 30 seconds later, or like Haiti, it could have been buildings nearly totally destroyed, and no scale really has a combination of all those factors together. Problem with the Mercalli scale, it is qualitative. It is a judgment call on how much has been destroyed, and also, if an earthquake hits in the desert, might be the biggest earthquake ever recorded on the Richter scale, but there's no damage because the sand just jumped up and down again, and that means that it's completely useless in terms of comparing it to other ones. So there's your 3 scales there, okay? How do we go about predicting and protecting and preparing against earthquakes? Well, there's a whole number of ways. You can read through these yourselves, but we can look at gases. We can look at how much the rocks are being deformed. We can look at animal behaviour, very, very short, but it does give you sort of 60 seconds alert. Seismic gaps, how often is likely to happen? Are there any little foreshocks? Now, remember, in Japan, they had 7 on the Richter scale 2 days beforehand, and they thought that was the earthquake, so that can be misleading in itself. But there's quite a lot of ways of looking for earthquakes, but you won't be able to pinpoint exactly when or where it's going to hit. That's the problem. might get like a rough guess, like we know there's one building up on the San Andreas and it could go any time. We don't know if that's going to be tomorrow or 15 years time, okay? So there's it's not perfect by any means. But what we can do well is we can prepare, and then we can put those plans into place and protect during the actual sort of event. So the biggest one being a seismic building design. Japan, in 2011, 75% of the buildings were already a seismic proof. Haiti, 0%. So there are all sorts of things you can do. Then inside the home as well, you don't want things falling on you. So in IKEA, how they give you the little things to attach bookcases to the wall so they don't fall on small children, that sort of thing. Shatterproof windows, earthquake kits, stockpiling in case of that sort of thing to happen, having that available in the house, knowing how to turn off the gas and so on and so on. And then planned routes for transportation to be able to get through, making sure, you know, if any bridges goes down, there's an alternative route in place, having teams prepared, trained for that, and education. You know, they have earthquake drills in Japan like we have fire drills. Drop, cover, hold. They know what to do should that event occur. So that obviously overlaps with the protection, where you are then using the kits, making sure your emergency services are getting out there for any relief efforts as soon as possible. So it overlaps quite a lot with that one. So that's kind of your earthquakes there, done very, very quickly. There's a little bit more about earthquake-proof buildings. You can easily look that up as well. We're now going to think a little bit about secondary hazard, but what our case study was, tsunamis. Okay, these tend to form at destructive boundaries. 90% of them are around the Pacific Ocean. And this is basically where you've got one plate going under the other, and the pressure is released after they've been stuck. It slips, and what that does is it flicks the water upwards. Now that means that the water above that point is higher than the surrounding ocean, so it's vertically displaced. And then kind of, you imagine that splashing back down and then ripples coming out, that's what's going on. So that raising in the water level and that certain point, that then has energy as it moves back down to its original level, and that energy is then transferred horizontally, leading to these tsunami waves. Now they are very different to your normal massive, like, destructive waves. They are huge. The wavelength of these is 120 miles compared to normally like a few meters in a destructive wave, and they can move at 500 miles an hour. And because of this enormous wavelength, it can take 30 minutes for one wave to hit before the next. So that's what's caught out a lot of people in the past, that they don't really let much out at sea. They're only a metre tall, like no bigger than your average wave when you're out in the open water. But then as you get closer, they do get much, much bigger. Hang on 1 second. No, it's fine. Okay, so sorry about that slight interruption there. So we've just done tsunamis. It's just left sort of one last bit to go. There is some information here about predicting, protection and planning preparation for tsunamis. So let's have a look at volcanoes to finish this off. So volcanoes are probably one of the easier hazards to predict. I might say they're the easiest one. So you've got a whole range of things that you can look at in terms of determining whether they're showing signs they're about to erupt. Key ones then, gas emissions, looking for specifically sulfur dioxide. They can use something called COSPEC, which is the instrument that they put in to measure the gas emissions and see if there's any changes. If the sulfur dioxide increases, then it's more likely that an eruption is going to be occurring. Ground deformation, basically, is it bulging? Is there any magma sort of building up underneath the surface? Are the key ones. There might be an increase in mass movements because of seismic activity. Those are linked. And that might indicate the slope angles changed, bulging, ground deformation and that sort of thing as well. So again, you can be prepared within the house, knowing what to do, making sure that the gas tank, the petrol is filled up in the car, and so on and so on. Place vehicles under cover if possible, so that the ash doesn't get into the engine and clog it, stop it from moving if you needed to evacuate. And then, like we saw, okay, attempt 3,966 to make this video. Okay, there's lots of signs. Read through them. Oh, that's earthquakes. So yeah, that's pretty much it. Yeah. Just have a read through, check that you know everything, and I think that will do.